Greetings everyone, welcome back to Trigonometry. Professor Simon here, ready to talk about sine and cosine graphs as functions. Okay, so where we left off in the last unit was how we can connect the simple definitions of sine and cosine from right triangles into a more generic system where I can deal with any angle. And then we generalized it even a little further beyond that, and we said if you can define the sine and cosine on the unit circle, like I have drawn here, then you can actually say that sine and cosine are a connection between a location on the grid and an arc length, an actual length of a piece of the unit circle as you're rotating. So this generic definition right here shows us that we can actually treat sine and cosine most generically as just some function of real numbers. It doesn't have to necessarily be about angles, right? At this point, we've generalized it to the point where t is just some measurement and x and y are measured locations. So it's really more of just input numbers, output numbers, just like any other algebraic function you've ever had to practice graphing with. So that's sort of the approach that we're going to end up with in these next few sections when we're graphing these functions. We can generalize our thoughts enough to the point where these are just more functions that you have to know that they exist. There's just some sort of input-output relationship between two variables, and these are the shapes that come of the way we've defined these functions. So all of the stuff that you've learned in algebra, shifting, flipping, stretching, doing all of the transformations of graphs are going to apply here. And actually, it would be good if you were rather familiar with those. If you are not familiar with those, feel free to pause this right now and run over to my college algebra series and look up the lectures on transformations of functions. Graphing through transformations is a very useful tool when studying functions of any kind. Okay, so the definition of sine and cosine with the unit circle. Because of the way this is a length 1 radius, the angle and the arc are always going to be the same number because it's angle times 1 gives me the arc length. And therefore, we can actually use the x and the y directly as sine and cosine, because it'd just be x over 1 and y over 1 when we're doing the sine and cosine ratios. And instead of the angle, I'm using t, the arc length. So really what happens is x is a real number, t is a real number, and they're just numbers in this relationship, right? Cosine is a relationship, sine is a certain relationship, and it has to do with the positions on the circle then. Okay, so then let's actually get the basic parent shapes of these things. And when I say parent shape, remember what I'm getting at is the shape that you should think of when someone says sine, this is the shape, or someone says cosine, this is the shape that you should be thinking of. And then the further graphing of these things by hand is doing all of the transformations, all of the shifting, flipping, stretching that you can do to these shapes. Okay, so let's get these basic shapes down. So sine is the y value. So what I want you to do is I want you to picture the point right here, okay? But we're going to start at 0. I'm going to start right here, and then I'm going to rotate like this, okay? So I'm going to rotate in the positive t direction like this. But I'm starting here. Notice when my t is 0, no rotation, my y value is on the axis. See, I'm going to go all the way down here, and my y value just rests right on the axis here. And you already know this. The sine of 0 is 0. So I have this point on my graph right here. Okay, next, let's go through another easy remembering point. Once I rotate to pi over 2 or 90 degrees, but I'm going to use pi over 2, remember, because radians is the connection, and that's the real number. degrees is not a connective number here. Okay, so 90 degrees is really pi over 2. And when I hit this, remember the y value is going to be the full peak there at 1. So at pi over 2, I'm peaking out of this graph right here at 1. Then I'll keep rotating to 180 degrees, which is pi. And notice I'm all the way out here, and my y has gone back down. As I'm rotating, right? As I'm rotating here, right? I'm rotating this way. So as I rotate, my y is going down like this. And then I hit 0. So it goes through this point. As I continue to rotate down this way, okay? I'm at 180 degrees and I'm going to rotate to here. My y value goes down to -1. All I'm doing here is I'm looking at the y value of these points, by the way. I'm looking at the points on the circle, but I'm only considering the y value because that's my sine function. Okay, then I get up to, I'm at 270 degrees. I'm going to rotate to 360 or 2 pi. And as I rotate there, right, I'm rotating this way. My y value goes back up to 0. Okay, so I'm back at 0 here. If you start graphing all of the other little dots in there, you'll see that these aren't straight lines. Because of the way of the circle works, it speeds up and then slows down, so to speak. Right? It has a lot of gaining to do, and then it sort of flattens out at the top of the circle. And then same thing over and over again. What you get is a function that looks like this. It peaks out, sort of like a hill. Then it goes through the axis and bottoms out in a trough type of thing. And then it comes back up to the axis like that. And that's what we call a sine wave. Okay? And we're going to talk more about the reason why we have the wave part of it there. But this is the shape that you should be thinking of when someone says, let's graph a sine, or let's graph a sine wave, or a sine function, or something like that. Okay? This is the shape that you should be thinking of. But here's the thing. There were several options that I could have chosen. Okay? From this point, the way I rotated was positive, right? I could have rotated negatively. Notice from here, if I went negative pi over 2, I would hit right here at negative 90 degrees, and my y value would be -1. So in other words, at negative pi over 2, I would be at -1. Also, after I've gone all the way around, all right, I could keep rotating another pi over 2. So 2 pi plus pi over 2 would be 5 pi over 2. And then I could keep rotating and keep rotating. I could keep going around and around and around. The thing you need to notice is that the y value is going to keep doing this. The y value is going to keep oscillating between the top and the bottom of the circle here. Every time the point goes around, the y value is just doing this. Okay? And what's going to happen is, since I'm going around the circle again, there's nothing new. There's no new values. This represents one go around the circle right here. This little stretch from 0 to 2 pi is one go around the circle. So if anything, I'm going to take these exact same values, make a little stamp out of them, and just stamp, 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 forever. Just keep going with that same shape. So that means at 5 pi over 2, I would peak out here, I would hit 0 here, I would -1 here, 0, then back up to 1, then back down to 0, like that. So I could fill in my shape sort of like this. I'm going to fill in this side of the graph, and now I'm going to fill in this side of the graph right here. Okay? Now, I kept the main piece in red there because I want you to think of this piece right here when you think of sine. But notice I can take this exact same piece and just stamp it here. And look, it's that same shape again. And then stamp it here. It's that same shape again. I could also pick it up and stamp it right here. It would be that same shape again. This is what we call a periodic function. A periodic function is something that takes a section and literally repeats that same section over and over and over again. And the section is a constant piece. It never changes in length. Once that piece is decided to be periodic, it periodically repeats that exact same shape. So you basically take it, like I said, and stamp it, stamp it, stamp it. And that length is constant. The length of the repeated piece is called the period. So you'll notice right here, from 0 to 2 pi is a period of length 2 pi. Okay? Now the 2 pi here is a length, the 2 pi here is a location. They happen to be the same just because we started at 0. However, if you take the difference between the peaks, let's say, pi over 2 to 5 pi over 2, it's a distance of 2 pi. If you take from this middle piece 2 pi to this piece 4 pi, again, that's a length of 2 pi. It doesn't matter where you start. Notice if I were to pick just some off point, like this point right here, I could repeat until I hit that same point again. And the length from here over to here would still be 2 pi because I'm hitting a corresponding point. Okay? And that's where this definition comes in. Anything that's periodic, if you pick a value x and then add the period length to that x, those two function values will always be the same. That's the whole purpose of being periodic. It oscillates a constant shape over and over and over again. All 6 of the main trig functions that we're going to talk about and graph are periodic functions because they are all defined on the unit circle. Sometimes we also call them the circular functions because of the way the trigonometric functions are defined to have that relationship of angles on the circle. Okay? There's actually an expansion of trigonometry into what we call hyperbolic trigonometry. We have hyperbolic functions and things like that, where instead of a circle, it uses a hyperbola. There's other ones along the same lines. All of the ideas are the same. But the ones you need to worry about are these circular functions, especially sine and cosine. Okay? So we have this periodic function of sine, whose period is 2 pi. It should make sense that the period is 2 pi. That's one full go around the circle. And then everything starts repeating again, right? Because then you're going around the circle again. Does it matter if you go negatively around the circle? No, negative rotation will still land you. This thing goes forever in both directions and just keeps oscillating over and over and over again. Let me give you a visual of how the sine is actually formed from the unit circle coordinate points. What you need to imagine here is that this unit circle I have is where all of the units are coming from, and this point is going to rotate, this green point here is going to rotate around the circle in a standard angle direction. So it's going to go counterclockwise like this around the circle. However, since I don't want my graph of the sine graph to move, I want it to just be stationary so that you can see it form, the actual unit circle is going to have to travel along the axis here so that it can graph the sine function appropriately. Okay, so the green dot is going to go around the circle, and then the circle is going to move along this axis here. Okay, so here we go. Notice as the green dot goes around, the y value just oscillates up and down. Okay, so where we're at here is 2 full periods of a sine. And notice that just letting the dot go around the circle 2 times has allowed the y value to just bounce between the values of 1 and -1 in such a way that they form a sine curve. And this is basically the idea of where that shape comes from. So let's do cosine. Cosine is going to be the x value. All right, so just like the y value, the x value is going to oscillate. I'm going to start over here and I'm going to rotate the point around the circle over and over and over again, right? So the x value is going to start moving this way. As I rotate, right, I'm going to rotate this way, the x value is going to follow it like that. And then it's going to rotate this way and the x value is going to follow this way. And then, again, the same thing. As I rotate, the x value this way is going to go like this. And then as I go this way, it's going to go like that. So the x value sits here and does this over and over and over again. The x value just keeps bouncing between 1 and -1. The only difference is, notice for cosine being the x value, when I have 0 rotation and I'm right here, I start at an x value of 1. It's all the way over. So I actually start on the top of the peak here at 1. And then by the time I hit the pi over 2, the 90 degrees, x has moved to the middle. And then when I hit 180 pi radians, x has moved all the way to -1. So to pi over 2, 0, pi, -1. 3 pi over 2, as you can guess, would be back to 0 because it's going to do this, right? As it rotates here, it's going to come back to the center. And then 2 pi, it's going to be back up at 1. So this is what the x did. It started at 0, and then pi over 2, pi, 3 pi over 2, 2 pi. And then it'll just keep doing that same repetitive motion over and over and over again. So here's the shape for this beginning one. Not my best. Hang on, I'll try again. There we go. I want you to realize that this is the same shape as that one. It's just moved over. It's shifted over by a quarter of a turn, a quarter of a period. Okay? See the peak and the peak? Notice if I were to just look at this piece right here, it goes down then back up. Same thing as this, down and then back up. Cosine, we always just remember, cosine starts on a peak. Sine starts at a center. But the rest of the shape is periodic, just like the other one. So this one goes to 0 here, then it goes through and back down. Whoops. Back up like this. It goes down and through, then bottoms, right, and then tops, and then bottoms. So it's like this. This. Again, it works the same way. The period is 2 pi. And it doesn't matter which point you measure from. If I go from one point to a corresponding point, that distance is going to be a length of 2 pi. The period of this function is 2 pi. It is a periodic function, and the length of that period is 2 pi. So it repeats every 2 pi. Okay? Another thing to mention is the domain here. For both of these functions, the domain is the entire real number system. I can actually say, let's get more technical here. The domain is the x values, right? So I have that x is an element of the real numbers. You can also here write negative infinity to infinity if you're more accustomed to the integral notation. However, the range on both of these is not the entire real number system. And that's one of the things we really need to point out here, because it shows one of our main trigonometric properties that we use a lot of times with sine and cosine. Okay, look at the graphs and notice the graph never goes above 1 and never goes below -1. None of the y values up here, none of the y values down here are used. The range is strictly y is an element of -1 to 1. And that's for both of these functions. That there tells you exactly one of our other little side identities that we always write, and that is that sine and cosine are both bounded functions. Sine of any angle has got to be between -1 and 1. And I'll use a different angle this time just for emphasis. Cosine is also bound. It really doesn't matter which variable I put here. I just want you to realize that whether we're talking about radians, degrees, just real numbers in general, okay, these are two bounded functions. Those values can't exceed that. So when you punch something in your calculator, sine of some angle, sine of some number, you will always get a decimal somewhere between -1 and 1. And that's what our graph here is demonstrating as well. One of the main things also, especially if after this, if you're going to be moving on to studying calculus and studying functions in more depth, another thing to realize is we use these for more than just angles. I said this earlier, I want to say it again. Realize that this is just a real number axis, and it is mapping the real numbers onto a small interval of real numbers, -1 to 1, right? It's taking any real number and just giving back some value between -1 and 1 in a certain pattern. And that's all these functions do. So from here on out in this lecture, you just need to know from here these two basic shapes. And then now we want to talk about how we can graph any version of sine or cosine given all of the different transformations that can happen, right? Now let's focus on being able to graph any of the sine and cosine functions that might come at you in your mathematical future by using the original shapes and then transforming them using the basic 4 transformations of stretching, flipping, moving, and then, well, we actually have 2 different stretches here, so that's why I said 4. But in any case, here I have listed out the 4 main numbers that you're going to always want to pay attention to. Okay, so I have trig here. Insert your trig function, whatever one you're doing, and it ends up being any of the 6 actually. Okay, so what I've got here is the setup in the structure that you're going to want to look for. In a little bit, I'll talk to you about how sometimes this particular parentheses structure is not always the way we like to see it, and we might have to do a little factoring. For now, this is the structure that we're going to be using, and if you're not there, I'll demonstrate when we have to shift and make it look like it's supposed to. So I've got what's called the amplitude. This is what I call the frequency. It's sort of a loose definition of the word frequency, and it helps you visualize exactly what this number does for the function. Okay, so I'm going to call the B letter here frequency, and then I've got the left and right shift, the horizontal shift, and I've got the up and down shift, the vertical shift. Okay, so if you're familiar with the transformations of the algebraic functions, this is practically the same thing, except a lot of times when they teach you the algebraic functions, they don't have the different horizontal stretching and vertical stretching. Usually they just do the vertical because most things can be equivalent in algebra with a lot of the vertical and horizontal stretches. However, trigonometry doesn't work that way because all of your multiplications cannot expand outside of your trig functions. They don't work as nicely as a lot of those other algebraic functions. So what the amplitude and the frequency end up being are your different actual stretching. The amplitude is going to be your vertical stretch. That's why it's multiplied on the outside of the function. And the frequency ends up being your horizontal stretch, if you will. And then horizontal shift also sometimes with these kind of waves will be called phase shift because of the way we use the word phase to talk about when waves can be working with and against each other. Okay, so for now, I'll just call them these things though. The two I want to focus on for this particular scene is amplitude and frequency. Amplitude is defined as the distance from the center line up to your peak when you're dealing with sine and cosine. Okay? Dealing with sine and cosine, the amplitude is literally the distance from the center to one of the main peaks or troughs, I mean, you know, lower peak, whatever. Okay? So notice sine x, right, the shape we just got through talking about, has a amplitude of 1 because there's a 1 in front of the sine x there. And the distance from the center down to the bottom there is -1 is the location, 1 is the distance. Same thing here, 1 is the distance. So if I do 2 times sine x, the distance is from 0 to 2, right? Amplitude is 2, the distance is 2. And if you shift, later on we'll talk about how when you shift, you have to shift the center line, because at a vertical up and down shift, this thing should not affect the amplitude. Your amplitude should stay where it is, and it should literally move along with the shifting. Okay, so whenever we shift vertically, it's the center line that we're going to move, because the amplitude has to be calculated from wherever your center line is. Also, another thing to remember is that the number in front of your trig can, or in front of any function really, can be something with a reflection, right? A vertical reflection can happen if a is negative. Okay, if you have a negative on your amplitude, it does not mean you have a negative amplitude. It's actually two different transformations. The amplitude is a stretching or compressing, and the negative is a reflection in the vertical arena there. So for example, -4 sine x. 4 is the actual amplitude, because that's going to be the distance from the center to the peak. And the negative just tells me that I flipped the actual function there, right? Instead of going up first, it went down first. If it were cosine, instead of starting at a top peak, it would start at a bottom peak. Okay? Next, frequency. Now again, like I said, this I have it in quotes there because it's not always called that, and sometimes there are other applications with trig functions that use the word frequency a little bit differently with a slightly different formula. Slightly different. It actually still relates to the same value. But in the real world, a lot of times sines and cosines and things like that get used as, say, for example, sound wave functions and things like that, where the word frequency actually has a physical meaning, and it's slightly different than the one I'm using here. And all I'm saying is I'm using this word because it is a very visual word, and it helps you understand what's going on in the graph. And then later on, if we need to use it for a different application, you'll see that the formula will just be something different for that particular application. Okay, and that, you know, that happens a lot in math. We have different genres with different applications with similar words. Okay, so for here, anyway, enough babbling. The word frequency is literally what it sounds like. How often this thing occurs, okay? Which is going to affect your period. The period of the graph has a natural length. For sine and cosine, it's 2 pi. The natural born length of one period of sine is 2 pi. Same thing for cosine. However, if you put a number inside of the trig function, like in this case I put a 2 on the x, so it's sine of 2x. It changes the period. It actually compresses the wave. Okay? And notice how it does that. Since there's a 2 there, it literally gives me two of the waves, see, 1, 2, in the same distance that normally one would fit. So look, here's sine normally, here's 1 from 0 to 2 pi. If I do sine 2x, it basically moves twice as fast. So I can fit two of them. Okay, 1, 2. So imagine if this were sine 5x, right? 1, 2, 3, 4, 5 in the same length. So what's happening here is this 2 pi is sort of etched in the DNA of sine. And that's because it's made on that circle, right? Circle is going to have your 2 pi rotational distance there. That's a natural built-in part of sine and cosine, okay? But it doesn't have to always be one cycle, okay? If you put another frequency number in here, the 2 pi is still a start and a stop. But the frequency number is going to tell you, hey, fit this number of waves inside of that 2 pi. So the 2 pi is always part of this. But the frequency number is going to switch it a little bit to say, okay, fit this many of them in that 2 pi length. So normally it would be 1, right? 1 of the waves in a 2 pi length. Or if it's 2x, it would be 2 of them. It doesn't have to be a whole number, guys. You could do sine of 0.7x. And it would be saying fit 0.7 of a cycle inside of the 2 pi. And that would slightly change your period length. Okay, the new period length, not the natural period length. Here's a graph of sine of x. And if I were to put in the function sine 2x, as you saw on the board, notice in the 0 to 2 pi section, that's from here to here, which is a natural period of sine, you'll notice exactly what we were talking about on the board. So here, let's get a better look here. So from 0 to 2 pi, notice the red graph actually fulfills 2 cycles. And it's because it's sine 2x. If I were to increase this to, say, 3, sine 3x, notice 1, 2, 3 cycles in the same amount of time that a normal sine would do, 0 to 2 pi. And again, these don't have to be whole numbers. If I change this to 4.5, okay, from 0 to 2 pi, notice that I'll get 1, 2, 3, 4, and then the top piece right here is half of a cycle, and then it hits 2 pi there. So this is what I'm talking about when I say that this is the frequency number when multiplied on top of the x there. It changes the number of times that this thing can appear in the 0 to 2 pi interval. So this is what's happening. However I'm putting, the cycles down, each one has to be equally positioned. Okay? If I'm putting 2 of these waves in, for example, I'm not going to have one short one and one long one. They have to be equally sized. So basically I'm taking the 2 pi and I'm making it into this many equal portions. In other words, I'm dividing it by 2. And notice the new period for the red graph here is exactly half of it at pi. Okay, so generalize that. Whatever b happens to be, the natural period 2 pi is going to be divided by that b. It's going to be divided into that many equal pieces. Also, vice versa. If you had to calculate b from a graph and you were trying to create an equation, you would divide 2 pi by whatever your period is, and you could actually get that b value back. Okay, so we'll be using this one a lot. For sine and cosine, right? That's where the 2 pi is. 2 pi is part of sine and cosine. Incidentally, secant and cosecant also. But tangent and cotangent are different. So when you finally get to that video a little bit later, you'll see. Okay, the 2 pi is because I'm specifically doing sine and cosine. In general, all periodic functions can fall victim to this same idea. But instead of 2 pi, it would be whatever their natural period is for whatever function you were studying. Okay, so let's get some examples. What I do when I'm graphing these by hand, and that's what I recommend you do with all of your homework, by the way, even if the computer that maybe you're doing it on software, maybe you're doing it by hand, maybe your teacher wants to see the handwritten graphs. Regardless, I recommend no matter which way you're doing your homework, you should handwrite all of your graphs. It enhances your ability to do the skill. It also enhances your ability to understand why the graph is placed where it is and where each important piece is happening in the graph. And then you can always translate that into whatever options your software has given you, or turn it in as your teacher instructs, whatever. When I'm graphing by hand, I always split my trig functions into periods that are split into 4 pieces. So I'll take a whole period, okay, and then usually that's what I graph unless I'm asked to graph 2 of them. We'll graph a period of one of these functions, but I always split it into quarters. Now think about that for a second. Why quarters? These things are defined on circles, right? And how many pieces do circles usually, right? The quadrants. And that's how our sines and cosines get most of their shape. If you go back to the last scene, I'll wait a minute. Take a look at those shapes. You can tell it's easy to split them into quarters because I did pi over 2, pi, 3 pi over 2, 2 pi, right? It was easy to split them into quarters like that. All of your trig functions are easy to graph if you can split one period into 4 quarters. So this is what I do. First thing I always calculate when I come to any function is, what is my period now? What is the period of this function? Not the natural, right? 2 pi is, the natural one, but it might be changed. So we calculate the period first. Then I calculate what I call the quarter period. Basically, I'm just splitting one period into 4 pieces. And that gives me the little marks that I want to put on my x-axis. And then that's where I start building my graph. So here, this is how it goes. I'm noticing 5 is my frequency here. Okay? So my period is going to be 2 pi divided by 5. Just using this formula here. I can't simplify that at all. It's just 2 pi divided by 5 is one whole period. Fine, that's fine, no problem. That means that my quarter period, remember I'm splitting it into 4 quarters, is just 1/4 times p. That's just 1/4 times 2 pi over 5, which I can get as pi over 10. Okay, now it takes 4 of those to make a whole period. It's a quarter period. 4 of these make one whole period. But that's going to help me draw this thing, you see. So watch. I'll just put my x-axis is how I always start my my trig graphs. I just put the x-axis, and I always put down 5 markers. 1, 2, 3, 4, 5. You can just take it whatever way you want. It's a slice of the x-axis, and I need 5 markers. The beginning marker here is always wherever your starting point is. The only exception is if you're doing tangent, in which case I use the middle one. Every other function, I start at the very left-hand side, and this is always my starting point. If you haven't shifted, your starting point's always 0. And if you go back to algebra, just think about that. That's always true. If I haven't shifted something left or right, we always start at 0, x equals 0, whatever. Okay? So that's what this is. This is going to be x equals 0. Incidentally, that's my y-axis, right? So I now know where my y-axis is, and I'm going to draw it in a minute. For now, I'm focused on my x values. Okay? So all the way. The reason why I drew 5 marks is because this is one whole period. Okay? So in other words, from here to here should be one period. Okay? That means that each one of these, you see, here's a section, 1, 2, 3, 4 sections. Those are those quarters. So that means each one of these jumps, when I go from this x value to this x value, I'm going to add a quarter period. So this number right here is going to be 0 plus pi over 10. So that's just pi over 10. Next, this one is going to be a jump, right? So it'll be pi over 10 plus pi over 10. Because I'm starting at pi over 10 and I'm moving a distance of another quarter. So that's 2 pi over 10. If you want to reduce, go ahead. This is how I count them. What would the next one be? If I add pi over 10 again, that would be 3 pi over 10. Next, 4 pi over 10. If you reduce 4 pi over 10, I hope you notice that you get 2 pi over 5, which is exactly the length of one period here. Okay, so let me get a few of those things out of the way. That's one whole period, right? I'm going to draw in my y-axis now. My y-axis is right here on 0. And then I pay attention to my amplitude. My amplitude is 3. So because I'm kind of lazy, I'm actually just going to put a mark and label it 3. And then I'm going to take that same distance down here and I'm going to mark -3. Because I haven't done any vertical shifting on this one, I simply know that I'm going to go from a center line up to this peak. Or I might start at a peak, it just depends, right? Since this is sine, I'm going to start in the middle and go up to a peak. Since it's positive, I'll go up first, right? If it was negative, I would go down first. So now I know these marks right here represent my quarters. In other words, my quadrants. All I'm going to do is draw the same shape. And this is the cool part of setting it up this way. I don't actually have to do anything different with the actual physical drawing of the graph. When I draw this sine function, I'm literally going to just repeat that same shape. It's going to start here, it's going to peak out, it's going to go through the center, it's going to bottom out, and it's going to go through the center again. And it doesn't matter how you have these labeled, okay? If you do this system the way I'm doing it, that's the points that you always hit for sine, because it starts in the center, goes up, middle, down, middle. That's what sine does. However, what's different between function to function is what these numbers are actually labeled. But we were easily able to count those just because I know the quarter period and each jump, right, is 1/4. So literally to draw this graph, I'm just going to draw it like a sine wave here. And it doesn't have to be, gorgeous. It just has to kind of look like it, right? So next question, what if they ask you to do 2 periods or 3 periods or a negative period of this thing? No problem. That's the reason why these marks are so nice. If I want to do 2 periods, then instead of 5 markers, I'll do 9 markers, right? A beginning and then 8 quarters. Okay? A beginning and 4 quarters is 5 marks. If I need 2 periods, I'll do a beginning and 8 more markers, so a total of 9. Or if you want to go front and back, after I've drawn this, I could just count 4 marks this way. The whole point of this is being able to count it. So if I want to do more here, for example, I probably won't be able to fit this, but you'll see what I mean. I'll take this same distance and I'll put more marks, right? This would then be 5 pi over 10 because I'm just counting by pi over 10. This would be 6 pi over 10. And then I would continue drawing my same shape, right? They would be the same sine shape. It would go up, it would peak out there, it would hit through the center here, it would start to bottom out at the next one where there would be 7 pi over 10 there. You literally just have to keep counting these quarter marks, and then you know how sine fits for each 4 pieces like that. Okay? So if you can figure out the period, the quarter period, and then you know where your marks are, you don't ever have to draw it differently. You simply know where each piece is going to fall. Now, to generalize this, well, what if I have to, put this in the computer? Well, after you draw this out, compare your numbers to where their numbers are, and you just got to line them up to see, what they're asking for, if they're asking for you to find a certain point on the graph or whatever. But once you have this, you have any number of cycles. Like I said, you could count this way, you could count that way. You just have to make it, work with whatever they're asking for. Let's do another example here. G of t is -2 cosine 3 pi over 2t. Remember, the first thing we do is we look for the period. In this case, my period is going to be 2 pi divided by 3 pi over 2. And I'm writing it horizontally division this time instead of the fraction because it's not an easy thing to put in a fraction. So think of it as, 2 pi over 1 divided by 3 pi over 2. So then I'll simplify that a little bit. That's 2 pi over 1 times 2 over 3 pi. The pi's will reduce, and I have 2 times 2 is 4 over 3. Notice this time our period doesn't have a pi in it, right? That's because our frequency does. So it kind of goes, back and forth there. Our period is now just a normal rational number. Okay, so let's do the quarter periods here. 1/4 of p is going to be 1/4 times 4 over 3, which in this case is 1/3. So this time we'll be counting 1/3 every time, or I'll be adding 1/3 every time. I haven't shifted here, right? I have not shifted. So when I put my x-axis on here, right, here's my x-axis, and I put my 5 marks, 1, 2, 3, 4, 5. Again, my beginning marker here is still 0, and that's because I haven't shifted it. Okay, this stays at 0, and the ones that aren't shifted like that, they're also very easy to count because I'm simply going to be counting whatever the quarter periods are. Once this shift is something different, then you start having to actually do some addition with fractions and possibly some common denominator issues. Okay, so 0 plus 1/3 is 1/3, plus 1/3 is 2/3, plus 1/3 is 3/3 or 1, plus 1/3 is 4/3, which we've already established is a whole period. Okay, now I need a y-axis, which we know is right here on 0. And my amplitude is what? I hope you just said 2, not -2. 2 is the amplitude. Negative means it has been reflected. Okay, and I know that it's a cosine. Let's see, I'm going to just make my little marker for 2 here and -2 here. Again, I'm just being lazy. You could actually count out the marks, or if you want to make your scaling the same, this would be really small compared to these big things, right? Because 2 is a lot further than 4/3. In any case, I'm just doing this lazily because I'm just going to draw that shape. I'm drawing the cosine shape. Now remember, cosine was the one that started at a peak and went down and then back up again like this. That was the cosine shape. And when you break it into quarters, right, it does this. And it has been vertically reflected. So instead of starting at a top, I'm going to flip this. It's going to do this now. It's going to go like this. So I have to start at the bottom, which means I'll be down here. Then it's going to go through a middle, the center line. Then it's going to peak out. Then it's back through the middle again. and then it's going to bottom out. So I have something that looks a little bit like this. Yeah, I know I could have done better. Let me do better. That's a good bit better. I know I nitpicked too much. Okay, so again, what if I have to draw more than one period of this? You could put more marks, right? 5/3, 6/3, 7/3, and then this pattern would just repeat. It's going to go, you know, back up this way. Or on the negative side, the same thing, right? It's going to come back up and go this way. But just like any other application, you just have to look at it and compare it, okay? What we have drawn here is one period of this function. If you need more than that, or if you need to change your scale or whatever, if you want to make your scale 1-to-1 and you know, actually count out these things like on graph paper and things like that, that's fine too. You'll actually see that this function should be looking skinnier, okay? I like to draw the graphs this way because it helps me ensure that I'm getting all of the important marks correct. Now I say important marks. Remember, it's important to know where these things bottom out and peak out. And it's also important to be able to know where their intercepts are going through the center lines there. Okay? And you'll notice those always happen on these quarter marks, right? The quarters tell you where the peaks, the bottoms, and the zeros of these functions are. So that's why it's easy to count these things with quarters. And that's why I do it that way. Now let me show you how these things look on the technology side, because it can draw these way better than I can by hand. Start with the first one here. I have 3 sine of 5x. And notice when you first punch this in, it just looks like a jumble. And this is really the reason why when you're graphing these things by hand, it's extra helpful to have those little quarter marks where all of the important features are happening. Just putting this on a plain grid where it counts normally 1, 2, 3, 4, 5. Notice I can't even tell where all of these peaks or bottoms of the graphs are. It's very difficult to see that. But if you know what way to number your axis in a more helpful manner, then you can definitely see these things. So first things first, I'm going to shift the axis outward some so that we can see in between the pieces a little bit better here. In fact, let me spread it out a little bit more even, like this. Okay, and then as we said before, the period on something with a frequency number of 5 is going to be 2 pi divided by 5. And then the quarter period of that ended up being pi over 10. So therefore, that's what I'm going to do. I'm going to come into this graph here, and I'm going to change the graphics so that my x-axis is being measured on a distance of pi over 10. And then you'll notice once I do that, you can actually make out a lot of the major features here on each piece. I'll spread it out even more right here. So take a look. Of course it goes through 0 because it's not shifted. And then now we can see exactly where this peak is at pi over 10. And it does have a peak of 3 because the amplitude is 3. And then it goes through the center again at pi over 5, which remember is 2 pi over 10. And it bottoms out at 3 pi over 10. And then technically this would be 4 pi over 10 where it would end this cycle right here. So there's a full period from beginning to end just between these two marks here for this guy. Okay, so now to move on to the next one, let's go back to the standard view, which I'll need to reconvert this back here. Okay, so again, -2 cosine of 3 pi over 2 x. Here's this graph, and just as before, it doesn't always have the same meaningful pieces, although this one's better than the last one because it is using whole numbers and some half numbers. So if I spread this out, we may actually get lucky here to see, without having to change the scale too much. I can see right here it does start at the bottom, as we said before, right? Because this is a negative cosine. The amplitude is 2. And I can almost make out where this top peak is right here. Almost. Let's see if I can spread it out a little more, if that will help. Yeah, not quite, huh? Can almost see it. It does, however, go through 1, as we speculated before, and it also goes through 3, as you can see. It's hitting these things in between cycles there. You can see it goes from bottom to bottom right here. This would actually be a full period, which we computed to be 4/3 is the full period here. And that's kind of why we're not seeing this, because these things are going to be based off of thirds. So again, let me shift the view here of the graphics on my x-axis so that I can, yeah, it's going to be off for a second until I get this punched in. Let's let it view everything in thirds now. Right, see now after I punch everything into thirds, you start seeing the places where this thing has all of those important features. Right? And that's because of the way the period is based off of the 3 times pi/2 there. Let's talk about the shifting transformations now. The horizontal shift, like I said, sometimes called the phase shift with these particular functions, and then the vertical shift. It just happens to be wherever you're adding or subtracting. If it's on the inside with the x, it's a horizontal shift. If it's outside and you're adding a number, it's a vertical shift. Now, let me repeat that. The horizontal shift has to be added inside directly to the x. Okay, it cannot be any other version of x. It can't be 5x, pi x, 9/2x, none of that. It must be x plus or minus a number, and then whatever that number is your actual horizontal shift. Okay, so you have to be careful. Real quick look. This one is not in that format. You notice it's something times the variable plus a number. Okay, sometimes you'll be given those to see if they can fool you, and that's why I have my example here for it. This number right here is not the true horizontal shift, and it must be accommodated. Notice the way I have my b multiplied outside of a parentheses. That's the format that you want to convert this into. Okay? So, this is what a shift in each venue does. We're always going to have 0 as our starting point, right? If I shift to the right or the left, all I'm doing is moving my x value starting point from 0 to whatever that h value is, because I'm adding it to 0. So if you have minus h, it moves to the right, and if you have plus h, it moves to the left. And so you can actually just look at that number, and whatever the shift is actually becomes your new starting point. So remember, I do my 5 markers, okay, and my first marker is going to be whatever that shift is, because that's where my new starting point has been shifted towards. If you have a vertical shift, then it simply moves the center line up or the center line down. You still have to treat it like the center. Notice the amplitude is measured from that new center line. It should have as much above and below as it would have if it was still on the axis. Okay? And sometimes your amplitude is smaller than the shift, in which case you'll have it all in one area like this. Or sometimes the shift is smaller than the amplitude, and you may actually go back through the axis. It just depends on the sizes, right? These are just a couple of visual examples for you to see. Whenever I'm doing these shifts, I still do everything in the same order that I counted before. So the horizontal shifts are accommodated by me doing the correct marker countings. I still do an axis, I still draw 5 marks, okay? The vertical shifting is accommodated after I locate my y-axis, and then I actually put the correct numbers on there, and then I'll either draw the function high or low. Okay, so there's not a lot of advanced thought behind these. You just need to know which direction the numbers are telling you to shift, and then you just need to make sure that all of your stuff is lined up properly. So let's get a couple of simple examples, and then after this we'll do a couple of examples where everything is all mixed together. Okay, so like I said before, this is not in a good format for us yet. I can see the frequency is pi over 5. Okay, but that's not going to help me when I want to start writing down my shift. So what I do is I factor. Okay, I'm going to factor b out of it. So then this is equal to cosine of pi over 5. Factor whatever number's in front of the variable. The number in front of the variable is your frequency. That's always the thing you want to factor out, no matter how messy it gets. Okay? The way that you calculate the factorization, the quick way, is to just use division. So to go from 2 pi over 5 to the factored number, just divide. Okay? By divide, I mean 2 pi over 5 divided by pi over 5. In this case, that's going to leave me with plus 2. Okay, so I won't be looking at this function anymore. I won't be looking at this one because it'll be misleading. I will be looking at this one. It's in this nice factored out format here, like this. My b, my frequency, is pi over 5. There's my variable. And then plus 2 is my shift. Since it's plus, it must be a shift to the left. Okay, so let's compute the period. Remember, that's always where we start. The period is going to be 2 pi divided by pi over 5. That means it will be 2 pi times 5 over pi, which leaves me with 10. And as before, I calculate the quarter period. So that's going to be 1/4 times 10, which is going to give me 5 over 2. Okay, so 5 over 2 is my quarter period length. The 5 over 2 in this case is not a location. You have to keep these straight. The shift over there, the plus 2, is a location. The 5 over 2 here is how big each of these gaps is going to be while I'm building the period that I'm going to draw. Okay, so here's my x-axis. I'm going to put my 5 marks on there. 1, 2, 3, and 4, and 5. Okay? The first mark here is -2. Remember what I said. Wherever the shift is, right? Normally it would have been at 0. It's been shifted to whatever that number is because it's plus 0. So in this case, -h because it was moved to the left. So this is 2. Okay, well that causes a little bit of an issue because remember, the distance from here to here is 5 over 2. I have to add 5 over 2 that way. Well, okay. I can convert to decimal, and it's usually a little bit not as good. What you do is you look for a common denominator, and then this is going to allow me to count. And it's going to make it easy for me to find all the rest of the marks. 2 over 1, 5 over 2. A common denominator would be 2, right? So here's what I'm going to do. Instead of negative 2, I'm going to write this as negative 4 over 2. It's the same value, but now it has a denominator of 2. And so my next mark right here is going to be negative 4 over 2 plus 5 over 2, which is 1/2. Right? Next, this mark right here will be that 1/2 that we're starting at plus another 5 over 2. So that's 6 over 2. If you want to write 3, that's fine. Okay? And then from here, notice all I'm doing is I'm counting by 5s. Okay? So 1 plus 5 is 6, plus 5 is 11, plus 5 is 16. If I wanted to keep going, right, I could go 21, 26, so on and so on. And if you want to reduce those fractions, that's up to you. Whenever I'm grading my papers, I actually don't care if they're reduced or not, because that's not the skill we're going for here. It is the correct value. 6 divided by 2 is 3, right? 16 divided by 2 is 8. Notice 16 divided by 2 is 8. From negative 2 to 8 is a distance of 10, which is what the period is. So I have the correct markers now. Okay? I need to discover where my y-axis is. Well, here's negative 2, and here's positive 1/2. The y-axis is wherever 0 happens on the x-axis. So it's got to be somewhere in between there, right? It would be a lot closer to the 1/2, since 1/2 is a smaller sized number. So then it would be something like this. And in my opinion, if you're a little bit off, that's not really what we're going for in accuracy anyway. Okay, so the only reason I need the y-axis is so that I can put my amplitudes on there. I don't even care if the y-axis is one of the important marks. And in this case, it isn't, right? The important locations are going to be these x values. Those are going to be my peaks, my bottoms, and my x-intercepts. Those are going to be the important pieces. Okay, so then my amplitude is 1, right? So if I just put a 1 and a negative 1, I'm ready to go. I'm going to be cosine, right? Cosine starts on a peak. So that's here. And then at the next marker, the important mark, right, it goes through the middle. Then at the next mark, it's at the bottom. Then through the middle. Then back at the top again. So my cosine should be something like this. And there's one period of that cosine wave. Again, same idea as before. What if I need 2 periods of it? I've got my marks, right? I can simply count 4 more marks and then just draw 4 more quarters. You can just keep rubber stamping this shape over and over and over again. And that's the nice thing about periodic functions. And the way we have this set up, I don't have to do much thought. I can just simply start counting here by 5s. Okay? Vertical shift. The vertical shift, I'm going to still start the same way as before. I want to know the period. I've got to make my x-axis. And then when I find my y-axis, that's when the vertical shift is going to kick in. Okay, so here we go. 8/9 is my frequency here. So my period is going to be 2 pi divided by 8/9. That's going to give me 2 pi times 9/8. So I can reduce this a little. I will have 9 pi over 4. Okay. My quarter period is going to be 1/4 of that, 9 pi over 4. So I'll have 9 pi over 16. is my quarter period. Now this time I don't have a horizontal shift. So it's back to the way we were doing them before. When I draw my x-axis here, I'm going to have my 5 marks, like so. And my first mark is 0, because I didn't shift it left or right this time, right? It's just in the center. The shift this time is upward. So then I'm going to be counting by 9 pi over 16 plus 0. So this is 9 pi over 16. Plus 9 pi over 16 again is 18 pi over 16. 27 pi over 16. 36 pi over 16. Basically, you see I'm just counting by 9s there. If you want to reduce them, that's fine. It just depends on your need. And now I draw my y-axis. My y-axis is going to go through the 0 mark here. Didn't have to look for it this time. Okay, so then I'm going to put my new center line. I'm shifted up by 3. So here's what I'm going to do. I'm actually going to count it this time. 1, 2, 3. And the reason for this is because I also need to incorporate my amplitude. Okay, so as you can see, my amplitude is only 1. So I'm going to have a really shallow wave here. I'm going to count actually up to 4. My new center line is plus 3. So here's my new center. Right? This is at 3. My amplitude is 1. So that means my function is going to fit no higher than this and no lower than this. Okay, well, I've already got my quarters labeled on the x-axis. I've got the center line, and I've got the high and the low line. This is a sine, so it's going to start in the middle. Then at the first mark, you see right here, it's going to be at a peak. Then at the next mark right here, it's going to be in the middle. Then at the next quarter, it's going to be at the bottom. Then the last quarter right here, it'll be back in the middle again. That's how sine works, right? So my sine wave is going to do this. Whoops. Come down some. And like this. And back up like that. Yuck. That's better. Okay, so a vertical shift is simply recognizing that my center is moved, and I just need to make sure that my high and my low amplitude are still measured correctly from that center. Just like before, let's go ahead and get a look at these two graphs that we were just discussing on the board. I have cosine of pi over 5 times the variable x. I can't use theta here. X works better for GeoGebra. Plus 2 pi over 5. And notice the computer is going to already know how to graph this thing. It doesn't even have to go through the factoring process here on this one. But here's what this one looks like. And, you know, it's nice and spread out. That's great. And I can see the peak here at 8. And I can see the bottom at 3, and I can see the peak here at -2. And that's actually what we needed to see. If you recall, we actually showed that this thing was shifted to the left by 2. And that's this thing right here. It was shifted to the left by 2, and you can see this was actually the starting point that we drew. The period was then 10. So we went from -2 at a peak all the way over to 8 at a peak. So for this one, since everything's counting in whole numbers, notice I don't have to really change anything unless I'm just more interested in these places where it goes through the center line, right? It's going through at 1/2 and at 5 1/2 there. as we stated in the board. Of course, if you need to see that, we would then change the graphics to talking about halves here. And then once you do that, you'll be able to see that this thing actually does go through the numbers that we calculated before, the 1/2 and the 11 halves there. So now the other one, sine of 8/9 x plus 3. This graph was shifted up by 3. And you can see this by looking at the center line is acting exactly like the axis used to. The x-axis was the same for us before we shifted it. It acted the same way. It's acting like the intercepts here, except this is not an axis. So this is what happens when you vertically shift. I actually shift my center line up here, and then it just oscillates around that line. The period, of course, the 2 pi divided by 8/9 did give me 9 pi over 4, right? So then we did pi over 16s were the intervals there. So let's actually take a look and see what happens when we change that around on our x-axis to 9 pi over 16, like so. 9 pi over 16 was our quarter period, and you can see right here the 9 pi over 16 is the peak. It was not shifted horizontally left or right, so it did start at 0 because it is a sine. It wasn't not 0, but it started in the center. It peaks out at the 9 pi over 16. This would be 18 pi over 16, where it goes through the center again. This would be the bottom at 27 pi over 16. Goes through the center again at, oh well, quite literally, it would be the 36 pi over 16. And there's actually the one cycle right there. Now let's get a couple of examples that have everything. F of x equals 3 sine of 8 pi over 5 times x plus 16 pi over 5, and then the whole thing with a plus 5 on the end. As usual, we want to start with the period. However, notice the parentheses are not adjusted correctly. I need to make sure that my frequency number is factored out of the parentheses. It's still going to be in the trig function. You can't factor it out of the trig function all the way. Don't make that mistake. But I do want that parentheses to have just x plus or minus a number. So I'm going to factor out the 8 pi over 5. 3 sine of 8 pi over 5 times. If it helps you, you can put a big old bracket here, and it'll be, you know, like this. Don't have to. Some people choose to. Okay, so right here for the number next to the x, not number, well, the number added to x here. Remember, I'm using division. I'm actually going to do 16 pi over 5 divided by 8 pi over 5. It's just a quick way to remind you, of how the factoring works. That's all we're doing is GCF factoring, but we're basically forcing the last term to have whatever we need by forcing the division there. You can see quickly this one resolves easily. It's just going to be 2 because it's just 16 divided by 8 basically. The pi's and the 5's eliminate. Okay, so now I'm going to do the period for my function. My period is going to be 2 pi divided by 8 pi over 5, which is going to give me 2 pi times 5 over 8 pi. So this is going to leave me with 5 over 4. 5 over 4 is the period of my function now. So I'm going to do my quarter period now. So I have 1/4 times 5/4, which is going to be 5/16. Rightio? 5/16 is my quarter period now. So let me go ahead and get my x-axis down here. I'm going to leave a big space because I'm noticing that it's going to be shifted up by 5. So I'll need a little bit of space above the axis there. Let's see. I'll use this as my x-axis. I'm going to put 5 marks on there. 2, 3, 4, 5. That's one period. I want to go ahead and graph 2 periods of this thing. So I'll put 4 more marks. 1, 2, 3, and 4. For a total of 9 marks. My beginning marker here is going to be my shift. In this case, it's been shifted to the left. So this is going to be -2 here. This marker has a value of -2. I am going to change that though into -32 over 16. Because remember, I need to constantly add the quarter periods to get from one mark to the next. So -32 over 16 has a value of -2, which is where my shift is. To get the next few markers, I'm going to continue to add 5, right? So this marker right here, it's going to be -32 over 16 plus 5 over 16. And then the marker after that, I'll add 5 over 16 again. So -32 plus 5 gives me -27 sixteenths. Add 5 again, I'll have -22 sixteenths. Then -17 sixteenths. Then -12 sixteenths. Then -7 sixteenths. Then -2 sixteenths. Yes, I know I could be reducing these along the way. That's not the point. As long as these denominators stay the same as the quarter period, I can just count by 5s. See, I'm just adding 5 every time. -2 plus 5 is 3 sixteenths. And then 3 plus 5 is 8 sixteenths. If you want to keep going, you can. I have fulfilled enough markers here to do 2 whole periods. And you'll notice that one of the reasons I did go this far was because between this negative and this positive, this is where my y-axis is going to be here. So I definitely want to be able to draw that in. It's going to be a little bit closer to the -2 sixteenths because that's a smaller size number. So it's going to be, about right here-ish. Okay, so there's my y-axis. And I have an amplitude of 3 and a shift of 5. So that means I need to think about this for a second, right? My center line is being shifted up by 5, and I need to be able to go 3 above and below it. So I need to go as high as 5 plus the 3 amplitude, 8. And I need to go as low as 5 minus 3, the 2. Okay? Then I'll have to count these out. Okay, so 1, 2, 3, 4, 5, 6, 7, and 8. Of course, I'm doing this, by freehand. If I wanted to really measure it out and get it nice and good, it would probably be a lot more accurate. But that's not what we're going for here. We're going for where is it located? Is it the right shape? Is it in the right direction? That sort of thing. Okay, so 1, 2, 3, 4, 5 is my center line here. And then I'm going to want to be between the 8 here. And the 2 down here. Okay. So now I have everything labeled. I can simply just draw my function in. So then I have a sine function and I'm starting on this marker here. So remember, sine starts in the middle. On this marker right here, I'm going to be right here. Then it's a positive sign, so it's going to go up. On the next mark right here, I'll be up here. Then at the third mark, I'll be in the middle again. Right? And then at the next mark, I'll be at the bottom. And then at the next mark, I'll be in the middle again. And then here, I'll be up at the top again. And here, I'll be in the middle again. Bottom. Middle, right there. And there we have it. 2 whole periods of the function 3 sine of 8 pi over 5x plus 16 pi over 5 quantity plus 5. So what's the domain and range on this function? Well, as we stated in the very beginning, the domain on the sine and cosine functions, as long as you don't put anything weird in the argument there, domain's going to be all real numbers. I'll use interval notation this time. What's the range? Well, the highest and the lowest, right? It's stuck in between 2 and 8. So y is an element of the interval from 2 to 8 here. No x-intercepts. As you can see, it doesn't actually get down to the x-axis this time. The y-intercept is not one of our easy-to-calculate spots. You would definitely need a calculator to find that. Of course, you could do that just by plugging in 0 for x, and then you would have to calculate that sine value. But as far as the graphing is concerned, as long as you have all the quarter marks, it's pretty easy to get the function to do what you want it to do. Okay, so let's do this next one here. I have -3 minus 4 cosine of the quantity 2t minus pi over 2. Couple of things. First of all, notice again, the parentheses is not in the format that we want for graphing these things. And on top of that, the vertical shift is written in a different spot. The vertical shift is not on this side, it's on this side. Does that matter? No, it shouldn't. It's addition. You should be able to add it in any order you want. Just don't miss some of the major details, right? The 3 is negative, which makes it a shift down. The negative right here is on the 4, which gives me a vertical reflection, right? So my thing's going to flip. And then, of course, the 4 here is my amplitude. So don't get those numbers mixed up and don't combine them. You can't do that either. First things first, I need to rewrite the parentheses by factoring. So I have y equals -3 minus 4 cosine of, I'm going to factor a 2 out because that's what will cause the t to be isolated. Well, not isolated, it's not the right word. The t to be something with a coefficient of 1. And then if I factor a 2 out of here, notice that what I'm really doing is a pi over 2 divided by 2. Because that's what I'm doing. I'm factoring out a 2 here. And that's the same thing as pi over 2 times 1/2. So then what I get is pi over 4. Now I'm ready. Okay, let's calculate the period of this function. So the period is 2 pi divided by 2, which is just pi. Okay, so then my quarter period is 1/4 times pi, which happens to be pi over 4. Hey, that's nice, right? The shift this time ended up being the same as the quarter period. And that happens sometimes. Sometimes it doesn't. Sometimes this could be like pi over 5. And then I would have to find a common denominator between the two. Anything could really happen here. Okay, I'm noticing that I have a downward shift this time. I'm also noticing that my amplitude is bigger than the shift. So I am going to be shifting the graph down, but it's going to come back over the x, well in this case the t-axis. It's going to come back over it a little bit every now and then too. So I'm going to keep my t-axis here sort of centralized. We'll do a t-axis here. Okay. I'll put my 5 marks on here. 1, 2, 3, 4, 5. Very good. And I'm going to start at the shift. The shift is pi over 4. To the right. Notice it's positive this time, whereas the last time it was a shift to the left. This one has been shifted to the right by pi over 4. Luckily for us, the quarter period is also pi over 4. So I don't need to change my denominator. I just need to start adding pi over 4s here. So pi over 4 plus pi over 4, I've got 2 pi over 4. Then 3 pi over 4. Then 4 pi over 4. Then 5 pi over 4. That's a whole period of this guy here. Well, where's my y-axis going to be, though? These are all positive numbers. The y-axis is going to be somewhere over here, right? Well, that means I'm going to count backwards now so that I can find it. Incidentally, on a side note, you don't actually have to put your y-axis intersecting your independent axis here. If it's too far away, if you feel like you're counting, like let's say this was like 101 pi over 4, and I'm counting by 1 pi over 4 to the left, it would take way too long to get there. It's completely okay if you want to do what we call an ellipse, or an ellipses of this, where you do a little squiggly line like that, and you just do your y-axis stuff over here, just to have the scaling. You want to have the y-axis somewhere. If it's too far away, it's okay to just break the axis and then just put your y scale somewhere where you can still register it with your graph. I don't have that problem this time. This time, I'm literally 1 mark away. Because a quarter period, one of these is a distance of pi over 4, I only need to go back by 1 mark. That's going to be 0, because I'll go minus pi over 4. Let's say we want to graph 2 periods of this thing. Do I have to put all 4 marks on both sides? No, I don't. This is going to be the main period that I draw right here. And then after that, I'll show you how we can connect up a second period where I do a little bit on each side. So I've got my y-axis now. It's been shifted down by 3. So 1, 2, 3. Okay, my amplitude is 4. So this thing's going to be huge if I continue the way well, let's do it. Let's do it. So then I need to go, from here, I would need to go 4 up, which is going to land me at +1. And I also need to go 4 down, which is going to land me at -7. Okay, so my new center line is here at the -3. And then of course I've got my high and my low. 1, 2, 3, 4 up, 1, 2, 3, 4 down. Okay, so let's draw these in now. I've got everything labeled for 1 period so far. Let's go ahead and draw up that period of this graph. I'm dealing with a negative cosine. Now remember, cosine typically does the round U looking piece, right? That's cosine. But negative cosine does this, because it's reflected. So I'm going to start at the bottom. And remember, my beginning mark was actually this one. I counted back 1 mark to make it work, but I'm actually on this marker here. And I'm going to be starting at the very bottom there, right here. And then next it's going to be in the middle, so that's here. And then on this mark it's going to be at the top, which is here at 1. Then it's going to be in the center again, and then it's going to be at the bottom again. So something like that. Over the long distances, my my free hand is getting lost a little bit. But if you do enough, you know, of the more than one cycle of it, you'll begin to really see the graph anyway. Okay, so if I want to do a second period of this, let's say I don't want to do all 4 marks to one side. You don't have to. Okay, as long as you keep in mind where your original cycle was, right? So you can say from here to here was the original cycle. Okay, I started here and I finished here. Now, I wouldn't always write that on my paper, but this is what I'm thinking. I can put like a couple of marks this way, and I'll count by pi over 4, right? So it'd be 6 pi over 4 and 7 pi over 4. I've already counted 1 mark backwards. I only need 1 more to get a total of 4 extra. That's going to be negative pi over 4 here. So technically I've put 4 extra marks on here. I put 2 to the left and 2 to the right. So when I have the full drawing of what I've labeled, I will actually have 2 total periods, 2 total cycles. So then here it's back at the center again, and at this point it will be at the top. So I can draw that in. Yuck. That really did not come out like I wanted it to. that's better. I'll have to draw the axis back again here. Okay. And then on the other side, something very similar, right? It's back at the center here, and then it's going to be at the peak up here. Give or take. Right? And of course, this thing's going to continue in this fashion. So I've got 2 complete cycles of this guy. Okay? So I hope these 2 examples help you see all of the different pieces that we can put into this. And let me just reiterate again that if you're doing this with a software homework and you're practicing for a test, I highly recommend that you just get the problem and graph it by hand completely like I've done here. Then come back and compare your graph to the answers that you're going to give or whatever. Because on most tests, this is the skill that you're going to need to have to be able to take that function and give your own version of the graph like this. Here's the 3 sine 8 pi over 5x plus 16 pi over 5 plus 5. So here's this guy. It was definitely shifted up by 5 because you can see my center line there going through 5, and it's oscillating between 8 and 2. Okay, so then let me move this down a little bit. We calculated a period to be 5/4, and we calculated the quarter period to be 5/16. So then what happens if I make my x distance measured by the 5/16 now? So then I'm going to spread this out so that we can see singular cycles a little bit better here. But I'm still not seeing exactly what I wanted, right? I'm not seeing that the marks right here for me to look at the numbers are on the important features like the peaks and everything. And the thing you have to remember is even though I got the correct distance, the graph was shifted off of the 16ths by a amount of 2. So 5/16 is not going to be exactly right as far as that is concerned. Okay, so I need to actually go ahead and change the scale into something a little bit more standard and readable. Let's go with just the 1/16 so that I can count all of the 16ths that I might need. And then let's try to stretch this out a little bit more so that we can get a better view here. And sure enough, you can see right here the point where this thing goes through right there. The -3/4 is where this point goes through right here. Right? And we were actually shifted backward -2 though. So this point right here is the original shifting point. And then I'm going to go 2 whole cycles, which is where the -3/4 comes in for the start of that second cycle, like we calculated on the board. And then you can see the important peak right here, and then the valley, the drop right here, are all on the exact same. This is -17/16, and this one right here is -27/16. It goes through the center line as we predicted at the -11/8, which is -22/16. And then of course we finish this cycle here just before the axis, or I'm sorry, just after the axis right here at the 1/2 mark. So in 16ths, that'd be 8/16. Okay, so let's go back to standard view and let's turn off this graph. Set my distance back normal again. The other graph was -3 minus 4 cosine 2x minus pi over 2. And again, this one was shifted vertically. It was shifted down by 3. So if I look at the center line here, and I can just change this one to -3. All right, there's my new center line for this graph. And it's oscillating between 1 and -7 there. All right, as predicted. And then it was shifted by an amount of pi over 4 to the right. Since it's a cosine and it's a negative cosine, right? That's what we expect this peak down here to be at the very bottom here. Right here. But I can't see that, right? And then, of course, the entire period length is going to be based off of pi over 4 as well. So let's take a look at using that as my marker lengths here. And sure enough, as you can see, let me stretch it out a little bit. That's exactly what we have here. We have this negative cosine function starting at the pi over 4, which was the shift to the right. And of course it hits the center line at the pi over 2, which is 2 pi over 4, peaks out at 3 pi over 4, hits the center line at 4 pi over 4, bottoms out at 5 pi over 4, and so on, the same way that we were predicting on our other model. So as you can see, whenever you're dealing with these things, it's all a matter of making sure that you have those major points for these things, the peaks, the bottoms, the center intersections, all on the important marks that you can tell where those numbers are happening. And then it's easy to go between by hand and technology and homework software. I want to finish up this lecture with one other version of the skills that we're talking about here, and that is to reverse engineer the function. What if you have a graph or data like this, maybe you have a list of points, and you would like to engineer or recreate the cosine or sine function that goes along with that information, the graph or the data. So it works pretty much the same, just in reverse, and it's actually a lot less calculating because I don't have to count. Some things are already going to be labeled, like maybe you were given the list of points, and sometimes you may actually have to look really hard at the graph and actually draw the dots in like I've done. Either way, one way or another, you should be looking for your quarters so that you can tell where your important pieces are. And the easiest things to do that with are going to be the peaks, of course. You can see where the very tops are, right, from here and then from here to here. That's really all you need to get you started. I can see that I have a bottom here at 2, and then the next time I have that same occurrence is here at 10. So it's easy to calculate that the period is just going to be 10 minus 2. The period is going to be 8 here, right? Okay, so once I have the period, I can calculate what that frequency number is supposed to be. My B is going to be 2 pi divided by the period. And remember, 2 pi is just because it's sine or cosine. Incidentally, that does work also with secant and cosecant, but not tangent and cotangent, and not in general for any periodic function. But since it's sine and cosine, I can do 2 pi divided by the period. That's going to be 2 pi divided by 8, which is going to give me pi over 4 for my frequency number, for my B. Next, I need to be able to calculate my amplitude. That's going to be as simple as finding the highest and lowest points. I know you can probably already see kind of where the center is, but don't always rely on that. Since these things are completely symmetric, what you do is you just take the very highest y value and the very lowest y value, and you can subtract them to get the full amplitude distance, which will actually be 2 amplitudes, right? So the height from the very top of the graph to the very bottom of the graph. Remember, that's two amplitudes because you have one up and one down. Okay? So at my peak right here, you can see I'm at 7, and at the bottom here, I'm at 1. So I'm oscillating between 7 and 1 here. My range is the interval from 1 to 7 is another way to say that. Okay? So 2a is going to be 7 minus 1, the distance between them. This is telling me that a is 3 because 2a is 6. So now I've got my amplitude and my frequency number. Okay? Since my amplitude is 3 and the bottom is at 1, I can see that the whole thing has been shifted up by 4. So along with the amplitude, I can see that I have a shift up 4. Now that I've calculated the amplitude, it's easy to just count from 1, right? 1, 2, 3. And my center line should be at 4. Okay, so those are the 3 things that don't change. Now let's talk about whether this is a sine or a cosine. What's the difference? Cosine would start at a peak. Sine would start in a middle. You have several choices here. Remember, cosine and sine are just off by a quarter shift. So if you're creating the function, you actually can pick either one. But you just need to make sure that you're picking the correct starting point to put the correct shift in there. So what I'm going to do is I'm going to write down a few different versions of the answer, and they're all correct. These 3 things, the amplitude, the vertical shift, and the frequency number, those don't change. But depending on which function you pick and whether or not it's been reflected, okay, you can pick any of these important points, any one of them. But each one will be a different function. If I start at a peak, this would be cosine. If I start in the middle, but it's going down at first, see how it goes down from this middle? If I start here, that would be a negative sine. If I start at a bottom, that's negative cosine. If I start in the middle and it's going upward, that's a positive sine. So I've actually got several choices here. Let's start with the peak one. This peak right here, I could have y equals, and I'll do y and x this time. This will be the y-axis, this will be the x-axis. Y equals 3 cosine of pi over 4 times x plus, now notice the peak has been shifted to the left, negative 2, so x plus 2. And then the whole thing was shifted up by 4. Okay, so that's one possible answer. What's another possible answer? If I start at this middle number here, I would say that it's negative 3 sine pi over 4 x plus 4. Notice no left and right shift this time because I actually started on 0. Okay, what's another possible answer? Y equals, if I start at this bottom right here, that's going to be negative 3 cosine pi over 4 x minus 2, because it's 2 this way, plus 4. Okay, let's get one more possible answer. If I start right here on this point right here, then I'll have y equals 3 sine pi over 4 times x minus 4, right? Because that's where the thing was shifted if this is my starting point, plus 4. Okay, so any of these are perfectly fine answers. They're all correct. They all represent the same graph. It really is just where you want to call, right, where you want to dedicate your starting point. There's not really a starting point in the graph. It goes forever in both directions. It's just where you want to call, your initial home. And a lot of times people would, of course, like this one because they want to see where it starts on an axis. Okay? So I hope this lecture has helped you see how to approach graphs of sine and cosine functions. Stay tuned for secant and cosecant in the next lecture.